Now that we know about valence shells and the ability to fiddle with the electrons in it, we have to talk about bonding, not the type of bonding that humans do. There are different types of bonds, but they all involve interactions with electrons in the valence shell. Atoms and molecules can share electrons, or they can just outright donate electrons to other atoms and molecules. And this forms chemical bonds. Conversely, they can also accept electrons, forming bonds. I mean, you can have you can't have one without the other, right? If you donate, there has to be an acceptor. When bonds are formed, though, they trap energy in them. And when bonds are broken, that energy becomes available for use. I have listed here the three bonds that we are concerned with in this class, and I've listed them from strongest to weakest. Now, when we get into defining these, we'll find that there are some subcategories for covalent bonds. Ionic bonds are exactly what they sound like, the attraction between a cation and an anion. It's like, I don't want to hold your hand, I just want to sit next to you. In this picture here, we have the ionic reactions that make these two salts, sodium chloride and magnesium oxide. So this here is sodium chloride, and this is magnesium oxide. Notice how the cation gives an electron, or plural, electrons, to the anion. It's as simple as that to make ions, and then those ions attract to each other. Like I said, there's no touching or hand holding. The ions just kind of like stand next to each other. That's enough to make an ionic bond. Ionic bonds, they are significant to us in this class because salts, which are electrolytes, are always being added to your body by way of your foods. When they hit your water-based blood, most salts dissociate back into their ions. Your body uses ions to move around thoughts. It's called an action potential, but we're not really there yet. A covalent bond consists of a pair of shared electrons, like hand holding instead of just standing next to each other. There's no movement of electrons from an atom or a molecule to another. The sharing creates this like super valence shell that surrounds both of the atoms, and this super valence shell provides each atom with the correct number of electrons in their valence shell. This box and these two boxes here on the right, they indicate the shared electrons. When two oxygen atoms come together, they share two pairs of electrons to make what's called a double covalent bond. So this is like holding two hands instead of one. And this is also what we call molecular oxygen, because it is two atoms glued together by a bond, and that is what is known as a molecule, two or more atoms. On the bottom of this picture, we have water, or H2O. The hydrogen atoms in the water are being bonded with a single covalent bond to the oxygen atom. This single covalent bond is weaker than the double covalent bond. So it would be easier, theoretically, to tear one of those hydrogens off of the oxygen than it would be to tear one of those oxygens off of the oxygens. But basically, the more electrons you share, the stronger the bond that you have. The participants in covalent bonding can share electrons equally or unequally. On the left here, we have carbon dioxide, which is, it's shaped like Princess Leia with the braid buns on the side. I think that that's what's happening there. Carbon is equally sharing its electrons with both of the oxygens. We can also see that there are two gray connecting lines between the carbons and the oxygens, and we can note that these are meant to note to you that these are double bonds. So when electrons are shared equally, such as in carbon dioxide over here, and this is CO2, this is what we call a double covalent bond. And when the electrons are shared equally, we can also call this a non-polar covalent bond. It's non-polar because no one area of this molecule has any type of charge. No positive, no negative. On the right is water, which does not equally share its oxygens among its atoms. Now, Princess Leia's braid buns are on the top or the sides of her head, making her Mickey Mouse. An oxygen atom has a greater affinity or attraction for the electrons than a hydrogen atom does, right? Right? This makes sense considering that oxygen has 7 more protons than a hydrogen atom does. And therefore, when a hydrogen atom and an oxygen atom share a pair of electrons in a chemical bond, the electrons actually, they spend more time around the oxygen nucleus than they do around the hydrogen nuclei. And that's simply because there's more protons down there. We can think of this like an electron party around the oxygen nucleus. And it's apparently the place to be if you're an electron. The significance here will attack us continually in this course. Nonpolar molecules versus polar, it's an important concept because, as the saying goes, like dissolves like. This means that polar substances will dissolve in other polar substances and nonpolar in other nonpolars. I guess we could also say that oil, a nonpolar substance, and water, a polar substance, don't mix. Because you're a water-based organism with the water as the basis of your blood, this can have effects on the solubility of things in your blood. For example, estrogen, testosterone, and other important hormones are nonpolar or hydrophobic, being made from cholesterol. How do they travel in your blood then? If they're nonpolar and your blood is a water-based polar substance? Well, they attach themselves to a protein that then creates a hydrophilic or a water-loving substance. And we can use this word, hydrophilic, which actually means water-loving, to talk about anything that dissolves in water. If you want to get, just one note, If you want to get an oil stain out of like a cotton shirt, you have to use a nonpolar substance to lift the nonpolar oil out of your cotton shirt. Baby powder is nonpolar, and it does the trick wonderfully. I know this because I'm kind of a messy eater. Before we leave the slide, over here, carbon dioxide nonpolar is also what we can call hydrophobic because it is a nonpolar substance and it does not dissolve in water. We just mentioned that the atoms of water are bonded together by covalent bonds. Keep that statement in mind because the molecules of water are bonded together by hydrogen bonds. Let me say that again. Molecules of water, meaning the entire Mickey Mouse head, are bonded together by hydrogen bonds. But remember the atoms, the hydrogens and the oxygens, the ears and the head, are bonded together by polar covalent bonds. These polar covalent bonds that unequally share their electrons, they create these poles on the molecule that are slightly charged. Because the electrons are having a party down here by the oxygen atom ends up getting this slight negative charge on all of these water molecules. Each of Mickey Mouse's ears have a slight positive charge because those hydrogen atom nuclei have just one proton in there, and its corresponding electron is, it's down at the electron party. Bummer. These slightly charged poles are what create the hydrogen bonds. The negatively charged poles attract to the positively charged poles. And this is why the covalent bonds that create these slight poles are called polar covalent bonds. Hydrogen bonds, which I just drew by my dotted lines. And sometimes I abbreviate these as H bonds, especially in like my own notes. But hydrogen bonds, they have nothing to do with hydrogen. Their naming has to do with how they were discovered, not anything about their structure. It's been hundreds of years. Why did we not change that? When you hear hydrogen bond, you should think of a really weak bond that can break and reform very easily. So no hand holding like a covalent bond. No, let me stand next to you like an ionic bond. A hydrogen bond is more like, I just want to look at you occasionally from across the room. As your water-based blood flows through your blood vessels, the water molecules are forming and breaking these hydrogen bonds between the molecules. It's that forming and breaking that allows water to take the shape of whatever container you put it in. The covalent bonds between the atoms, remember, they're strong. They never break and reform. Just the hydrogen bonds between the molecules. Hydrogen bonds they're abundant in your body because your body is, like I said, a bubbling cauldron of reactions. If you were made mostly of covalent bonds, it would be really, really hard to lose weight since those covalent bonds are really strong and take a lot of energy to break and reform. Hydrogen bonds, they're also responsible for creating bonds between areas of one molecule. Proteins are really huge molecules. That's my picture of a protein right there. Make sure you draw it exactly as I did. But proteins have slightly charged areas of their molecules as well because they're so huge. And what ends up happening is that the protein, the negatively charged area, don't draw that. The protein, its negatively charged area, can bend back and bind with a positively charged area. So these folds, the bending, is secured by hydrogen bonds. And this is what we call intramolecular bonding. Intra means within the same molecule, right? So these proteins that have areas that attract, that are secured, and their final shape is made by these hydrogen bonds.